Okay, good morning, nerds. Today's tutorial is part 2 of the first-person shooter tutorial. We are definitely building off of the tutorial that we did last time, which was the first-person shooter 1, in which we made a lot of prefabs. For this tutorial, we will be working primarily on getting movement code working. We've already set our cameras and everything, so just as a reminder of where we left off in the last tutorial, again, nothing works, we just made a bunch of prefabs, but we do have things from a third-person view when we run our game, and we can see the enemy up in front of us. We've got our player directly in front of us, and theoretically we should be able to move around right now. We don't have the code for that yet, but that's what we're going to be working on today. So that's going to be our goal for the day, is to get, or for the tutorial anyways, is going to be to get that movement working. Again, this does build on the previous tutorial, so if you haven't completed that one yet, things aren't going to work. Also, if you were doing this previously without setting up these things first, because I'm using a prefab, it is important to note that the position of all of my game objects, and this is very, very important to note, if I switch up here on my top bar, if I switch my view, my toggle handle position button, it's currently labeled center, and the two options are center and pivot. Center will attempt to grab the rough center of an object, but pivot will grab it by its actual point and location. And if you notice, both my player and my enemy's pivots are in the floor. If you've done things differently, your pivot position, which would set your positions, may be in the center of these capsules. And honestly, for the entire tutorial, and for all of this entire project, as long as you're consistent, it should work. So if your enemy is set up so that this pivot is more centered inside the capsule, and your player is set that way too, your tutorial should be fine. But if you followed the tutorial for just the player, for example, and didn't do it for the enemy, and you've got one where the pivot is centered and one where the pivot is on the ground, you are going to have some problems. So it's very, very important that they match. In this case, for the tutorial, since I did start from scratch, I did them both the same. In fact, if you recall correctly, I cloned my player into my enemy. And so they are both consistent. So that's an important thing to note. What you'll see if you do that incorrectly is the player should move just fine, but once we start doing the enemy's AI, the enemy will tend to drift towards the player. So if the enemy's pivot is down here and the player's pivot is more centered, the enemy will actually start floating. And inversely, if the player's pivot is on the ground and the enemy's is centered, the enemy will start going into the ground. So either way, you get some weird behavior that we don't want. And by setting the pivots equally, either both in the center of your object or both on the bottom, you'll do fine. So just some notes before we get going. So for this tutorial, we are going to be doing some fairly weird setups, and this is more to teach different movement styles. You may want to jump ahead a little bit if you want like perfect movement, but I do want to teach a couple of different ways to do movement. One of them is by using our directional vectors, which is the better way to do things. But I also just want to use this as an opportunity to teach some basic movement skills. And basic object manipulation, since for a lot of the people watching this tutorial, this may be your first experience with Unity code. So we're going to start off. One of the main things that we do need to do is we need to prepare Visual Studio, which is going to be our code editor of choice for this project. You can totally follow this code with other things. I am using Visual Studio Community. That does bundle automatically with Unity. If you just do a basic Unity install, it will ask you to install Visual Studio Community. But you can use other products such as Visual Studio Code, JetBeans Writer Editor. Technically, even a product like Notepad++ will actually do the job. But you may not get some of the context highlighting and some of the other stuff that works, that makes Visual Studio kind of the optimal way to work here. So I am going to be using Visual Studio and walking through the tutorial as if Visual Studio is your main programming environment. Again, specifically Visual Studio Community as opposed to Visual Studio Code. Also, Visual Studio Professional will work the same way as Community for the purposes of these tutorials, but Code is a little bit weirder. Visual Studio Code, the product, not code itself being weird. So those are just some considerations. Okay, so one of the main things that you do need to make sure of, especially if you're using a network managed device, as many students watching this may be, is that Visual Studio does not necessarily install itself into Unity as the desired code editor, and that can cause a lot of weird behavior, including your Autotype options that I'm going to teach you later. IntelliSense will not work correctly, and so we want to make sure that we get that settled right from the very beginning. So what I'm going to do is, I am on a Mac, so I'm going to use the Unity menu and go to Preferences. But if you're on a PC, I'm not positive, but I am fairly certain that you would use Edit Preferences. And if I recall correctly, it shows up down in here somewhere to do this exact same operation. So I'm going to use Edit Preferences or Unity Preferences. But if you're following along at home on a Windows device, I think it is Edit Preferences. So inside of there, I'm going to get this Preferences window. The two things that we're going to look at today, the first one is External Tools. If you have Open by File extension, which is not the default usually, but on some of your systems it might be, you need to make sure that you switch that to Visual Studio. And the rest of the defaults that will pop up here as soon as this is done completing, these defaults are usually pretty good. You can mess with them if you know what you're doing, but it's a good idea to just leave them alone unless you're positive you know what you're doing. The other thing that we're going to do is go into colors. And by default, you have one labeled Play Mode Tint. It's about the fourth one down, and it's a light gray by default. This is a tint color, so I'm going to just caution you ahead of time. Keep it in the pastel range. It is definitely going to make things a lot easier for you. But what we're going to do is change this. So I'm just going to drag over here, and you're going to see I've got like this nice level of pink here. We do want to keep that nice and light. Again, pastels are going to work way better for this. You can like a bright color if you want, but this color will not work very well for you. This bright red. So we are going to definitely move here in this pastel range. I've got it kind of about a quarter of the way down, about a third of the way in. And then you can pretty much pick any color along the wheel. I'm going to go with a purple this time. I tend to go with red, but this time I'm just going to use a purple. And this is going to tint. And the reason we want this, it's worth noting, especially as we're testing code and we're changing settings and things like that. When we run our game now, what you're going to notice, I'm going to go ahead and get out of preferences. I don't need this anymore. But if you're still messing with colors, you might want to leave it on. Is when I hit play, the entire Unity interface is going to turn a different color. Because I'm using a lighter tint, I can still read, this may not show up well at home, but I can still read all of my settings and all my values. They show up in that lighter purple, which is fantastic, but it's definitely going to show me. And the reason I want to do this is, I'm going to just demonstrate this really quickly. You don't need to follow along with this. This is just a warning. Is, for instance, if I change a value right now, so I'm just going to move, I'm going to just move my player up to a Y value of, I don't know, 5, just so he's like flying in the air, and I play. That value is going to take effect, which makes some sense. And I'm going to undo and look at that. He's still up in the air, and I'm going to play again, and he is still up in the air. And some of you at home may be thinking, okay, what kind of crack is this guy smoking? But this does have a valid reason. So now what I'm going to do is, again, I'm in the air. I'm going to play, and I'm going to put him back on the ground. He belongs at 0. We're going to put him at 0. I'm going to hypothetically mess with some other settings in here. So on my rigid body, I'm going to mess with some of these constraints. And again, I don't really want you to follow along, but I've basically inverted all of these constraints while the game is running. So you'll notice that I'm in this purple screen. And as soon as I click, I click stop, you're going to notice that all of those settings went away and I'm back to floating again. Nothing you do in the inspector matters while you're in play mode. And there's some good reasons for that, but basically we need to be really, really careful. I will often edit values in the inspector to test something, but a lot of times people will go through and they'll adjust something just perfect in the inspector, and then they'll stop playing and then realize that they've just lost everything. And so it's really, really important to just be aware, am I playing the game or am I not playing the game? And having that play mode tint, so it turns purple on me, is a great way for me to realize, like, I do have to kind of squint a little bit at these words, and that just reminds me, oh, I'm in play mode, my changes are not going to be retained. So I can tinker with things, but they're not going to stick. So when I'm not in play mode anymore, I'm going to go ahead and put my player back on the ground again. So I'm going to set that position back to 0Y. And now I'm back on the ground and I can go ahead and get to work on my true goal, which is coding movement. So we're now going to do add component. We're going to, we're going to click on our player's inspector. Because we are going to be adding some code to the player to get movement working. We're going to do add component. And because we don't have a script already, we are going to type in player script. And I'm going to go ahead and hit enter. And that is going to open up, the Unity is going to realize that that doesn't exist. And usually Unity knows, hey, if something doesn't exist, there's a good chance you're trying to write a new script. And a script is just a chunk of code that is going to control something. If you are a C# programmer, you will recognize this as a new class derived from the monobehavior parent class via inheritance. If you're a newbie and didn't understand any of that, that's okay. We're gonna learn as we go. But we want to go ahead and add this new script. It's called player script. We're going to say create and add, and that will create our very, very first script. Now we are going to do a little bit of house cleaning before we get going because I do want to stay organized. So I'm going to go back to my project tab, and right now in my script or in my assets folder, I do have this player script, and you can see the £, that's for C#. It is written as C £, but it's verbalized as C#. And we're going to go ahead and create a new folder as we have before. We're going to call this scripts, and we're going to drag that player script in there. Now it's more safe to edit. So I'm going to go ahead, and you've got a few ways, just like everything else in Unity. We have a few ways we can edit it. I can go into the scripts folder and double click on player script, but more commonly I'm working in an object, and I just want to access it from there. Rather than going and hunting for it in the inspector. So the easier way to get to this is if I'm in an object and I need to mess with its script, I can find that in the inspector, and it has its title bar, but it also has in the script box, it has player script. I can double click on that, and that's going to open up my Visual Studio Code editor. You'll notice that that opened quite quickly, and I do have this new behavior script. You can ignore that one. That shouldn't be there. I put that in there so I could load Visual Studio up and have it running before I started the tutorial. You'll notice that my Visual Studio loaded pretty much instantaneously, and that's because I already had it running in the background. When you first run it, it'll take a little bit longer. The nice thing is I can save as I go and leave Visual Studio running, and then use my Windows and Tab key to flip back and forth between windows. Or on Mac, that would be the Command button, or Open Apple for us old people that are used to doing it that way, and the Tab key. So it's pretty much the same thing, only you use the Command instead of the Windows key. All right, so now that I'm in my code base, I'm going to walk you guys through quickly what different code chunks are, because I'm assuming that people watching this are beginners. So you may be already kind of familiar with some of this, but we have a few sections of our code. The first one is called our using section, and my analogy for usings is they're effectively, C# and Unity specifically is very, very vast. There are so many different chunks of code that do different things and functions and libraries and all kinds of stuff. And if you were to put all of those in a project, you would bog it down so badly. It would take up, hundreds of megabytes of RAM and hundreds of gigabytes of RAM perhaps. And it would be just enormous. And you'd have some very, very serious performance problems. So what C# and Unity both do is they give you, by default, a very limited collection of tools in the way of functions and libraries, with the idea that you can add more as needed. And the way that we add more is via these usings. And so the three that Unity will always start you off with is systems.collections, which gives you access to things like lists, which are very, very prevalent, and we'll be using them quite a bit through the course of this tutorial. Not today, but in future installments. Systems collections generic, same deal. That's going to give us some listability. And Unity Engine, which comprises the bulk of our Unity scripts, and is very, very critical for this, which is the monobehavior parent class. And monobehavior is basically the primary way that Unity is able to interact with scripts. There are some other ways to do this via a system called ECS, or Entity Component System. That is way beyond the scope of this tutorial series. We will not be looking at it. And it is really for the more advanced programmers. But for most of us, monobehavior is pretty good. And so we have a public class. That just basically, class is a definition, meaning that this object, this is how we're going to define and refer to this object. And inside of that, we have two functions, otherwise known as methods. We have a start function and we have an update function. Those, again, are given to us by default. There are many, many, many more functions that monobehavior gives us access to. These are just two very, very common ones, and so Unity just puts them in by default. The start function, as the comment implies, will call before the first time that the first frame of our program, or as soon as the object is created, and update will be called sequentially every single frame. And at this point of time, we should talk about what a frame is. A frame is a frame. A frame is basically one screen redraw and the code that happens in between each one. So a typical game will have approximately 60 to 90 frames per second, depending on the detail of the game. And with 60 being slightly more common, but a lot of games are rapidly moving towards 90, especially on the higher end consoles. And it is occasional where you'll get more than that. But we can think of this like we think of if you've seen animation, or if you've seen when people draw flip books and things like that. Each frame of that flip book, there's going to be code that runs in between and handles our gameplay code. So we need to think in terms of frames. Unity defaults to 60 frames per second. So anytime we're thinking an update, we need to be thinking about the fact that this code will run presumably 60 times per second, or approximately every 16 milliseconds. So given that, we are able to do start, which is going to be one frame at the very beginning, and then update, which will be the first and every subsequent frame from when the object is created. So that's kind of a quick tour of what a script looks like. And it's also worth noting here for newbies, these curly braces are very, very important for holding your code together. And it is very important that they are maintained vertically. So you can see that I have an open curly brace after the player script is created. And it has a matching curly brace when it is all done. I have a start function with an open curly brace and a matching closing curly brace that is indented from there. And then after that is finished, I've got a void update with a starting and ending curly brace. We need to maintain curly braces, hashtag respect the curly. And inside of a curly brace, every time you open a new one, you want to do an indentation. So for example, and you don't need to follow along, I'm about to delete this code, but if I could do something like, for example, if x is less, whoops, I don't even want that. I'm going to do if x is less than 3, that would have a curly brace below it. And you'll notice that I'm indenting even further, and maybe I do a debug log here. And again, you don't need to follow along or even understand what I'm doing here, but you'll notice that everything inside the curly braces is indented, my curly braces match, and then we go out again. And this was referred to as nesting or levels or layers. There's a lot of different names for it. But it's very, very important that we keep things indented correctly. It's going to make errors easier to spot. But basically the rule is always, if I open one, I should see a closing one directly underneath of it with nothing in the way. And everything inside of those two curly braces would be indented from there. It makes troubleshooting a lot easier. It makes your code a lot more legible. If you do happen to get things out of sorts, so for example, I do something like this, and this is just a right jumble. This is terrible. You should never have a code that looks like this. But if something like that happens, as long as your curly braces are correct in at least what lines they're on and everything, you can delete the last curly brace in the sequence and put it back. Whoops, I made a mistake there. But if you delete it and put it back, Visual Studio will make its best effort to align things correctly. So that's a kind of a way we can kind of put things back together if we have trouble. And you'll see me use that trick a few times, especially after a copy paste or something. So there's kind of our layout. Now inside of the class, we can have variables, and variables are going to allow us to do some things. And then we can also add additional functions as needed. And functions will tie to either system behaviors such as update tying to each frame being updated, or we can write functions that just are our own thing. Like for example, we will be writing a take damage function that when the player or the enemy gets hit, it will allocate that many hit points worth of damage to the character. So we can write our own functions, we can use Unity built-in functions. It's really a nice extensible system. So what we're going to start with today is I want to do movement, and I want that to happen kind of all the time. Like if a player hits a key on a specific frame, I want that key to work. So so that means that we need to be doing that update because we need that to happen every single time. And we're going to start off small. So I'm going to be implementing WASD movement or WASTA movement. With the idea that W is going to be forward, A is going to be strafe left for now, S is going to be reverse, and D is going to be strafe right. We will later on add Q and E for rotate left and rotate right respectively. And I know most of you are probably screaming at the YouTube right now saying, oh my God, what is he doing? You're supposed to use a mouse for that. We will get into mouse controls later, I promise, but for now I'm trying to keep things limited to the keyboard for simplicity's sake and for you guys to learn. We will add mouse controls later that will make everybody happier, but for now we're going to be using perhaps an awkward keyboard layout to be handling that. Because our game doesn't have verticality, ordinarily I would use space for jump. We won't be worrying about that in this game because we won't be having any verticality. So let's go ahead and get some started. The very, very first thing that we're going to do is we're going to do an if statement. And if is the core for all decision making in code. So we're going to start off with an if statement, and if requires conditions. And conditions go inside the parentheses and represent whether or not we should run a specific branch of code. So in this case, we want to say, hey, if the user is pressing the W key, we should be moving forward. So the code for that is going to be if, and then in parentheses, we want to use the input class, which is capital I. Anytime we're using a class, it's going to be a capital letter. So we're going to be using the input class. And this is a great time to teach you guys about Autotype. So you will notice that I've only typed in the I and the N in input, and you'll see that IntelliSense is attempting to say, hey, I think you mean input. The cool thing is if I agree with IntelliSense, yes, that is what I wanted to do, I can immediately move to my next piece of punctuation. For instance, if I hit the space bar, it's going to fill in the word input for me, and it'll type the rest. Using this, I can type a lot faster, and it will also reduce the number of errors that I have because I'm less likely to make a typo. So I'm going to backspace over that. And because we want to use subcomponents of things are identified using the dot, which is the period. And so I want to access part of the input function or input class. So I'm going to do input. Again, I'm going to start typing. I see that. I want a dot next. So I'm going to hit the dot, and that will fill in input, put in my dot, and start asking me, what do I want now? The thing that I want to be checking now is get key, which is going to ask me for keyboard input. And for now, I'm going to say, hey, get key down. This will not be our final thing, but for now, we're going to do that. And get key down is a function that will tell me yes or no, is a certain key pressed. And for all functions, and you'll get used to this as we go, you need to use parentheses to give it parameters, or even if there is no parameters, you still need the parentheses because they identify this as a function. But what we need to do is we need to use key codes. So every key on your keyboard will send a binary or numeric code to the device whether that's a computer, tablet, whatever, saying, hey, the user hit this key. Rather than having to memorize them, Unity has some built-in enumerations that will identify those keys for us in a way that is a little bit friendlier using the key code class, which actually I think it's an enum, which is an enumerated list. So it's going to convert those values for us and make it something that we can do friendly. So the key code for W is keycode.w, capital W. And so I'm using tab to lock that in. And that will convert, so instead of having to say 10111111 or whatever it happens to be, I made that number up, so it's probably not accurate. We can just type in keycode.w and not have to memorize all these binary codes for things. So if input is keycode W, if that is true, it's going to run the things inside my branch. Now, what I want to do is I want to move my character. If we look at Unity for a second, and you don't have to follow along on this because I am going to tab back to code here in just a moment, but if we look at any game object we have, every single object has a component in its inspector referred to as a transform. That transform has three key components: position, rotation, and scale. By manipulating these, I can manipulate an object. For instance, if I want to move the player forward, you're going to notice that the Z value is currently -776. If I move it forward, I am now at 4.93. So by increasing that value, I'm moving forward. So we can access the transform, and then we can access the subcomponents of that transform. We can also access via another means, we can access things like this capsule collider we put on, rigid body, even the player script. We can interact with different components by accessing their components and then accessing their properties. So the property we want to access is position, which is a property of the transform component. Fortunately for us, all game objects do report out on their scripts. They do allow us direct access to the transform. So we can just simply say, hey, transform, we want to access your position. And specifically, since we're hitting W, I want to access the Z component of my transform. So I'm going to do transform.position.z. And what I want to do is I want to add to its current value. And we can do this a couple of different ways. And you're going to hear that phrase a lot in Unity and a lot in programming in general. There are so many ways to do every single operation. Mathematically in Unity, actually in programming, if we use equals is an operator. And so if you're thinking about this in math terms where both sides are the same, just get over that. What we're doing when we use equals is we're saying, take this thing, in this case, transform.position.z, and make it equal to the thing that's on the right. So if we wanted to add to that value, we want to increase that value, which would help us move forward, we could take the current value of transform.position.z and add another value. For example, maybe I'm going to say 5. And that's perhaps a little bit crazy in this particular instance, and you'll see why in a second. But basically, this is going to allow us to change. Oh, and actually, I'm sorry. We have to do this a little bit differently. I misspoke that. We can't quite do it like this. We have to alter the vector entirely. So position is a vector. I forgot we are not allowed to edit subcomponents of the vector, so we can say transform.position equals transform.position, and we need to add a new vector and just add to the v component. So we're going to say plus, and we have to create a new vector, and this requires learning some vector math, which is a little out of scope for this particular tutorial, but I think if you follow along, it'll probably start making sense after a little while. A vector is a type of value. Think of it very, very similar. It's different, but think of it very, very similar to how you think about the coordinate system. If you've done any geometry at all, the coordinate system, you basically have typically an x and a y value. With a vector 3, you have x and y and z values. So we're going to add to our current position, we're going to add a new vector that is going to be a vector 3. And it does have an x and a y and a z value, which we can specify. In this case, we only want to add to our z. So we're describing this as what we would call a delta or a change. So we're going to say, hey, well, if I want to move forward, I don't want to change my x at all. So we're going to say 0. I don't want to change my y, so we're going to be 0. And the new value that I want to add to my z, we're going to say 5 for now, which again is a little bit big. And so this is going to take my current position, which has an x and a y and a z. It's going to add 0 to my x, 0 to my y, and 5 to my z. So we're going to go ahead and test this and see what happens. So I'm going to do a file save. I'm going to switch back to my Unity using Alt Tab or Windows Tab, depending on which kind of computer you're on. I'm sorry, on Windows that would be Alt Tab, not Windows Tab. And on a Mac it's Apple Tab. And so now we've got this script is on my project, and if I hit the play button and I hit W, you're going to notice that I can move forward, but I have to tap W every single time I want to move. That's not desirable behavior, but at least we are moving forward. And if I click on my scene view and I zoom out a little bit, I can see that every time I hit W in my game view, I am moving a little bit further forward in my scene view. Not optimal. This isn't exactly what we want, but it is working. So let's figure out why it didn't work the way we wanted it to. If we go back to our code, we will notice that, okay, so our vector worked beautifully. 5 does seem to be doing the trick. 005 does seem to be moving us forward. But you'll notice that I'm using, and I did this deliberately, but we used key down. What we really want here is we actually want to move, get key down is going to register every single time you have an instance where the key was not pressed before but is pressed now. So it's only going to trigger on a key press. Alternatively, key up will trigger when you release a key. Those two functions are fantastic. If I'm doing something like a charge up attack, I might start my charge when I press the key down, add to my charge while the key is pressed, and then release the charge when my key goes back up again. But really, for movement, this is pretty silly. what I want to do is, like, while I'm holding the key, I want to be moving forward. So the code for that is just simply get key. If I use get key, code W, I'm going to go ahead and run that code just the way it is. All I've changed is get key down to get key. So I've just deleted the word down. I'm going to go back to my Unity. It will reload the script. I'm going to go ahead and hit play again. And now, this is a little bit better, but I just flew through the scene. So we definitely need to slow down a little bit. I'm going to reduce my speed considerably. Remember that if we look at Unity, let's go back in there for a second. If we look at Unity, I'm at position 674. If I move 5 forward, so I'm just gonna go to -174 for a second. That jumped me this far. And keep in mind that we make that kind of movement, because it's the update function, 60 times per second. So I am moving at a rate, if I move forward 5 in one tick, I move forward a grand total of 120 per second, which is pretty darn far. So I definitely don't want to do that. So we're going to tone this down a little bit. I'm going to go back to -6.74. I want to be kind of tucked back here again. But what we're going to do is we're going to slow this down. So instead of 5, we need to reduce that. We need to divide that by about 60. So I'm going to just do 0.5. I'm 0.5. 0.5, that's dividing it by 10. Let's divide it by, let's drop that down to about 0.05. And because this is what we call a float value, which is a floating point number, Unity uses floats as opposed to doubles. So if you're already pretty familiar with programming, you may know the difference between these two things. But float is a less sensitive number, which is good for game programming. We don't need the precision and we do need the speed. Double requires more processing power, but we have to denote it using the F key. So 0.5F means it is a decimal value, sort of, good enough for our descriptions today. It's a decimal value that is 0.05 and it is a float. So there we go. Now our function is safe. Again, I'm going to save that. And for you guys at home, it is a good idea to get in the habit of using save all, not just save. And if you're using a Windows Visual Studio, up here in your area here, there is usually a disk icon that represents save. And then there's a disk with another disk behind it. That represents save all. And so you should definitely get in the habit of hitting the double disk to save every time you need to work, because that is going to save all of your open files. Later on, we are going to be having some things in future tutorials where we jump between chunks of code, editing both along the way. It's important to save all of the code, not just the file that you have open right now, not just the one that we're looking at. So again, we're going to pop back to Unity. It's going to rebuild. I'm going to go ahead and hit play. And this should be a lot better. That's maybe a little too slow. We could probably speed that up a bit, but it is working. And so the next thing that I'm going to do is I can't move backwards or sideways or anything else. So we're going to go ahead and fix that. And for this, we're going to use my good friend copy paste. And copy paste is a fantastic thing in programming. We should use it as much as we can. Not only does it make our speed increase, if we have functioning code, by using copy paste, what you're doing is you're replicating good code. There's less likelihood of typos, there's less likelihood of other problems. So I encourage you to use copy paste for everything. One of my mantras as a programmer is be lazy. Lazy programmers are usually efficient programmers. And again, you're going to be a lot less likely to introduce errors in your code. So since we have forward working, we can copy that. So I'm going to use Control Z, or Control C rather, and Control V. And I'm just going to paste this 3 more times into my code. And we're just going to edit these. So my second one, I'm going to deal with backwards next, which is going to be my S key. And we're going to do the exact same thing. Actually, you know what? I'm sorry. We're going to delete all that. I forgot I was going to teach you guys one more trick before, so we're going to delete all of that. The next trick that I want to show you is the plus equals trick. And here's how that works. Anytime that you're setting a value to the same value, I'm taking transform position and I just want to add to it. If we're doing a basic arithmetic operation to the same value and setting that, we can skip over some code. There's a programmer shortcut. Instead of doing transform.position plus, because we're already doing that, we can do instead, we can get rid of all of that code and simply do plus equals. And what plus equals means is take this, add this, and then set it equal to this, which is a great way of doing an increment. So all we're doing here is we're adding, plus equals means add this to this. So this is a lot more efficient code-wise. It's easier to read. It's easier to see what's going on. I can do the same thing with subtraction, which we're going to do in just a moment. And I can also, to an extent, do that with multiplication and some other operations. So we're going to copy paste this now for realsies this time, I promise. We're going to paste that 3 times. Again, I'm going to alter backwards next. Now to move backwards, what we want to do is subtract z. So instead of position plus equals new vector, we're going to do position minus equals new vector. And that will give us a subtractive effect, which will move us backwards. And for now, you will notice, I think we can move, actually, I'm not positive if we can move through walls or not. I think we can, but we'll be fixing that later. And then I'm going to do the exact same thing here. I'm going to do the D key, which is right. Now for right, what we want to be doing is we don't want to be increasing Z. We want to be increasing X. Because X is our left and right, or yeah, X is our left and right. So positive X is right. So by pressing the D key, what we're going to do is we're going to add 0 to D, 0 to Z, but we're going to add 0.05 F to the X value instead. And then we're going to do the exact same thing down here for the A key. So we're going to switch our key code to A. And we're going to add, or we're going to take 0.05 F. Our Z is again going to be 0 because we're dealing with the X axis instead. And instead of plus equals, we're going to do minus equals, which will of course subtract that value. So if we press D, we will add to the X, which is going to increase or move us to the right. Minus, if we hit A, is going to minus us this much, which will move us to the, I'm sorry, I think I misspoke last time. Adding should move us to the right. Subtracting should move us to the left. Okay, we're going to go ahead and save this. I'm using my key codes for that, so I'm going to do a Control S or an Apple S, and I'm going to move us back to Unity. And again, it's going to compile. I'm going to hit my movement. And I can move forward, I can move backwards, I can move left, I can move right. And okay, I am stopped by the wall because of the rigid bodies that we installed last session. I had forgotten that we had done that already. Normally when I teach this, I don't teach rigid bodies first, and so we can still move through the walls. But fortunately, that rigid body is pushing back on us a little bit. So we're already pretty good. Now, the one thing that we can't do is we can't turn. And that is something that we do want to be able to do. So what we want to do for turning is, and I actually forgot my notes here, so I need to pull something else up really quickly. So I'm going to pause just a moment. Uh-oh, I can't find pause. Okay, so we're gonna keep on going here, and I'm just gonna do this live. I'm gonna open up a different project that has my notes. Whoops, that is not what I wanted. Oh, I already have that open. Okay, so we are going to take a look at another project that is also a first-person shooter. And I need to pull up my notes on this because I forgot to pull them up already because I am a bad streamer. You can go ahead and comment on that in the comments if you want to, but I'd rather you don't, please. Like and subscribe me anyways. I promise I don't suck all the time. All right, so I'm going to pull up my comments here, or my other code, and I'm going to move that into my other window so I can walk you through it without you having to always look at it. What we're going to be doing here, there we go, is a transform.rotate. So again, we're going to look at rotation. So I'm going to pop back to Visual Studio again, and the rotation code. Again, we're going to bind this to the E and Q keys, which is a little awkward. It's not a normal key binding, but again, we're going to do this instead of dealing with the mouse right now. So again, I'm going to do an if statement. I'm going to basically copy what we've done before, input.getKey, and I'm just going to use regular getKey because, again, I want it to work while we're holding it down. I'm going to do keycode dot, in this case, I'm going to do keycode dot Q. Actually, I'm going to do E first. E is going to rotate us to the right, and that's going to be positive rotation. So that's why I'm doing that one first. And in our code, now this is a little bit different. One would think that we could just simply add to our rotation, just like we did with our position. Theoretically, that ought to work. What we're going to find, though, is that it doesn't work out as well as we would like. So what we end up needing to use instead is, because rotation is stored as a quaternion, which is a pretty fun word. I'm going to spell it out here on the screen for you. This is not code that we're going to use, so please don't copy me. But there's our word of the day, is quaternion. Quaternions are very, very specific forms of matrices. And unless you're an advanced math student, they are something that we should stay away from at this level. Not to be scaring people off, and I do encourage learning at all times, and you are definitely smart enough to handle it. I believe in you, but it is a very, very advanced topic, and it is very, very out of scope for this tutorial series. So instead, what we're going to do is, instead of calculating quaternions on our own, we're going to use some Unity built-in functions that will do this for us, and save ourselves the calculations. So we are going to use, transforms also have a rotate function built right in. So we're going to use this transform.rotate function. And the transform.rotate function needs to know what rotation you want to put in. And so for us, what we want to be doing is, if we look at our game object, we want to figure out which axis we want to rotate around. Now for us, we have an x-axis, which is the red one, we have a y-axis, which is the green one, and we have a z-axis, which is the blue one. And if we hit our rotation button here, which is the second one, or the E key, I can start grabbing things, and you'll notice that if I grab the green one and move it around, that is rotating us side to side, which is kind of what we want here. Which makes some sense, because if we look back at these arrows, and I'm going to repair my rotation and put it back to 0 again in the inspector, but if we look at our arrows, it makes some sense. If we rotate Y, it means rotate around the Y-axis. If we rotate Z, it's around the Z-axis, and if we rotate X, it's around the X-axis. This is aligning with the concepts in flight of pitch, yaw, and roll. Pitch, if we think about this, is, and these align, pitch, yaw, roll is X, Y, Z, and X, Y, Z is RGB, for those of you who are familiar with the red, green, blue color system, so it's easy to remember. So if we think about pitch, pitch is X rotation, which is red. And if we think about somebody pitching forward, we think of them lurching forward and falling kind of flat on their face. And if I move the x-axis, you'll notice that my guy does indeed pitch forward and start falling on his face. So that kind of makes some sense why X is pitch. And you'll notice that we are rotating around the x-axis. Again, I'm going to reset that to 0 for the next discussion. If we grab the Y rotation, which is again green, This is called yaw, and if you're not a pilot, you probably don't really hear that word, but yaw is a sideways rotation, side to side. It's basically turning. So if we look at this, yaw rotation is great, and I think we can pretty clearly see right now that yaw rotation is the one we want, which is again rotating on that Y. But I'm going to rotate it, or I'm going to hit 0 and talk about roll, which is Z rotation. Again, we're rotating around the Z axis. That's the blue handle. And roll is rolling around, which kind of makes some sense to us. Again, we think about rolling. If we want to do a barrel roll, we're rolling around in a circle around our forward axis. So these all make sense. Pitch, yaw, and roll. Again, yaw might be an unfamiliar one, but pitch and roll really make sense with normal grammar. Okay, so we're going to go back into our code armed with the knowledge that we need to do yaw rotation. And what we're going to do here is we're going to rotate around, or rotate by, again, a new vector 3. And in this case, we want to be changing the Y value. So I'm going to do 0, comma, let's rotate by a fairly small angle. I'm going to do 3 for now. That's a pretty little angle. Again, because we are going to be doing this 60 times per second. And then I'm going to do I'm going to do another 0 for my Z. Now, the rotation function does have some extra builds and things like that. The one that we're going to be using is rotate 3. And we do want to think about, we've got our Euler angles, which is EULER is pronounced Euler. And we're going to do relative to ourselves. So we're going to do space.self is the default for that. And that's a built-in tool, so we're just going to use that. And that should give us a pretty decent rotation. And I'm going to go ahead and just copy-paste that entire thing. So again, Control-C, Control-V. And I'm going to change that to Q. And again, I'm just going to invert that, so that's going to be a -3. We're going to do File, Save All. We're going to go ahead and run this. And we should see ourselves, when we run it, we can turn. That's a little fast, but that's great that we are able to turn. Now, here's the deal, is this looks pretty good moving forward and back, but here's the weird thing, is if I go sideways, but I move forward, I'm moving at a weird angle. So this is me pressing forward right now, and this is definitely not what I want. We definitely need to be fixing that. And the reason that this isn't what I want is because Z, if you remember, is us moving along the Z axis. But here's the thing, is if I rotate this way, I'm not facing the Z axis anymore. I have my Z is forward, but the world Z is different. So what we're going to do here is we're going to stop that. We need to be thinking about that we need to be thinking about how to move along a rotation. So we're going to have to change what we have. So really what I want to do is, instead of moving along this vector, the vector that I want to be adding when I move forward is our forward vector. Fortunately for us, our transform actually does acknowledge what we would call the local Z, which is transform.forward. So instead of doing what we're doing here, I can do + transform.forward. And that's going to work. And so I'm going to do the exact same things down here. I'm going to say -. Now, unfortunately, there is no transform.back or transform.backwards or any permutation thereof. So what I need to do is, instead of adding transform.backwards, I'm just going to subtract transform.forward, which is going to look very similar to what we already have. Again, I'm going to type this in, transform.forward. And then we're going to apply the same basic theory to my left and my right. Right is going to be transform.right, which is again another vector that is pre-generated. It aligns perfectly with our local x-axis. And then again, I can subtract it, which we're already doing, to give me a left. There is no transform.left, but I can use negative transform.right. Okay, this should get us a lot better. So I'm going to go ahead and save. We're still not perfect, but we're getting a lot closer. And this is going to give us, again, once we compile, this is going to give us, I can move forward still, although now I'm going quite fast. I'm going forward, and you'll notice I am still using forward and back. And as I move different directions, this is working. Now I am also teleporting through walls. That's probably not healthy. Please don't try that at home. And that's not very good. But I also can strafe left and right no matter which directions I'm going. I'm hitting my left and my right keys. That's working pretty well. Forward and back is working. At any angle, things are going pretty well. Now my problem now is that I am moving forward by my transform.forward vector. Transform.forward is guaranteed to have a distance of 1. So I'm moving forward 1, but if you recall correctly, the last pass, we had to move at a speed of 0.5. So I have a couple of options, but this is a great time to stop doing extra work. So if we notice, one thing I could do here is say, well, instead of transform forward, I'm going to multiply transform.forward, and star is always multiplication in programming, times 0.05f, and that would take us back to our original speed. I'm going to go ahead and test this. You don't need to do this at home because I'm immediately going to get rid of it. But again, just to test it and show that it works, now when I move, I'm moving back to that slow speed that I was doing a second ago, but it's the desired speed. My backwards is still set to a magnitude of 1, so if I move backwards, I'm going to move backwards very, very quickly. Forward, not so much. In fact, I don't think I'm going to be able to move through this wall. So I can move backwards through the wall, but I can't move forward through it. And this is a good time to say, why am I able to run through walls, Jim? The reason we're able to move through walls is because movement happens via effectively teleportation. And collision isn't checked in the in-between, it's only checked in each relative location. And so, and it'll push you out if you're not able to be there. Well, what's happening is I am moving so fast that I'm just skipping over those walls entirely. And so I'm never actually hitting them, so there's nothing to stop me. One moment I'm on one side of the wall, the next moment I'm on the other side of the wall, and a collision was never registered. So that's not going to work out very well. We are going to be doing some things to fix that though. Okay, so I'm going to go back into my code. Now here's the thing, and why I told you don't bother typing this in. We're going to be messing with these values a lot, and more importantly, we're going to be messing back and forth on the code, and I don't want to have to readjust these every single time, times 4 every time I want to plug something in. We also want to give our designers, we're acting as a programmer for this entire tutorial series, but we actually want to let our designers modify things straight in Unity rather than having people have to access the code base directly. So what we're going to do is we're going to create a variable. And a variable is simply a box in the computer's memory that we can hold a value in. So what we're going to do instead is we're going to go up just below our public class definition. We're going to jump down. We're going to give ourselves a couple of blank lines here. And we are going to do float. And we're going to just create a float called speed. And that's going to create what's called a floating point integer, which is going to give us a decimal value. We've talked about that a little bit a few moments ago. And we're going to assign that. We're going to say it equals 0.05f. And now, if we ever need this number, we can refer to it as speed instead. But that also means that if I ever need to change speed, I can change it here, and it will change it anywhere where speed is referenced. So instead of transform.forward times 0.05f, we're going to do transform.forward times speed. And I'm going to do that on each of these. So I'm going to multiply each of these by speed. Here we go. I'm going to put that space in, even though it's not strictly necessary. And here we go. I'm also going to do the exact same thing with our rotation. So I've decided that the rotation is 3. but we may not want to leave 3 in as our final number. So instead, I'm going to go float. And we often use abbreviations, and we use a thing called camel case. So I'm going to change rotation angle. Our variables always need to be one word and one word only. So I'm going to instead abbreviate that. Instead of rotation angle, we're going to call that rot for rotation angle. So that's going to be our rotation angle. And you'll notice that I'm using capital letters to denote individual words, but I'm always starting with a lowercase letter. The convention is that variables have lowercase letters and functions have uppercase starting letters. This is actually referred to in the industry as camel case. And if I did something like, please don't follow along with this one, but if I had a function called start function, you'll notice that I have capitalized every word, including the first word. This is referred to as Pascal case. But I don't want to mess with that function, so I'm going to immediately get rid of that other word and leave start alone. So rotation angle is now in camel case. We'll be referring to that as rot angle from here forwards, and we're going to set that equal to 3. So again, we're going to go back down into our code here, and instead of 0, 3, 0, we're going to do 0, rot angle 0. And negative, we can actually do this. Negative rot angle. Whoops, cannot type today. Negative rot angle, there it goes, 0. Okay, so we're in good shape here. We've got our transforms, we've got our rotation angles. Things are doing pretty good. And so now we can go into Unity. Whoops, I can save that. And now the nice thing is we're going to go back to, this is a little too slow if I click play, but the nice thing is all of my speeds are now slow. I'm kind of moving around in a box right now using all 4 W, A, S, and D keys. Q and E are, if anything, maybe a little bit fast. And my new goal is, just like I can adjust things in the inspector for my transforms, I can adjust things in my capsule collider. I want to be able to edit these values in the inspector, and I can't currently do that. And by allowing them to be edited in the inspector, that also means that prospectively, I could just let a designer edit my objects in Unity if I'm partnered with someone else, and they would never have to touch my code, code is a place you don't usually want designers to be. So I'm going to go ahead and go in. I'm going to look at my code base, and the way we can make a variable accessible to Unity and to everywhere else is by using the public flag. So I'm going to change this to public float speed and public float rot angle. I'm going to save that and go back into Unity again. And what you will notice, I'm going to go back into Unity again. There we go. And what you will notice is that now in my inspector, I can see speed and rotation angle. And now I can change those to something else if I wanted to. If I want to, I can change this to, let's go back to 5 again. And when I hit play, I am moving very, very fast and teleporting through walls, and look at me go. I can, while the game is running, I can actually start adjusting these down. So I'm going to adjust this to 1. And that's still pretty quick. I'm not really happy there. But the nice thing is I can be adjusting this while the game is playing. Find a speed that I like. 0.5 is still clipping me through walls, but it's a little bit better than the 0.05. I'm going to try 0.1, and that's giving me a pretty nice movement. I could go a little faster than this. Maybe let's say try 0.2. Whoops, that's still 0.1. There we go. 0.2. That's a little fast, so we kind of need to start figuring out, kind of finding that sweet spot. 0.1 feels like I've got some movement, but I'm not clipping through walls anymore. That feels pretty good. Again, I'm not going to back up through a wall. Oops, I did back up through a wall. So 0.15 isn't very safe, so I feel like we should probably stick with 0.1. And then I can do the exact same nudging. Now, reminder, it will terminate, or it will revert back to its old values when I stop. So now I need to keep track of the fact that I've used 1.5, which I feel the best about 0.1, so we're going to leave that. But when I stop my program It did jump back up to 5, so now I need to manually type that 0.1 in again. And then I could do the same adjustments for my speed, or for my rotation angles. But we're gonna leave those alone for now. Now, here's another problem that is invisible to us right now while we're in play mode, but it would be exposed as we encounter things like lag. We do need some lag compensation. So what we have been assuming is that we are running at a perfectly even 60 frames per second, and we're moving speed accordingly. What we're gonna do instead is we're going to calibrate for what happens if a frame isn't 60 per second. Now, nicely for us, and this is very, very different from the old days in which the processor speed made a radical difference on the speed that your character moved. I used to play games like Crystal Caverns and Commander Keen back in the 90s, and if you got a fast enough processor, briefly tapping on a control button would make your character like sprint across the screen, and we don't want that anymore. And especially with variance in computer speeds and things like that, we really want to be able to keep that nice and even to give everybody kind of the same play experience when they hold it down, no matter how fast their processor is. So what we're going to do is we're going to go back into our code, and we want to calibrate by time.delta time. So delta is a fancy word that is used in science to mean change. And so what we want to do is we want to multiply this by the change in time as measured by milliseconds. So really what we're going to do is we're going to say, hey, I want to move X number of distance per second, and then we'll multiply that by the number of milliseconds that have passed. And what that's going to do is that will scale it back down again. So we're going to actually be using quite a bit faster speeds, but we're going to be multiplying them by a decimal value, which is going to shrink them. So to implement this, we're going to go and add to our equation. So we have currently transform.forward times speed. We're going to multiply that also by time.delta time, which is in the time library. And I'm going to copy paste. So I'm going to grab my multiplication sign and my time.delta time, but not grab the curly brace, or I'm sorry, the semicolon. And we're going to go ahead and put in, whoops, that did not work. Hang on, Control Z, Control Z. We're going to go ahead and put that in. So I'm going to do, again, Control C. We're going to go back to the end and do Control V. And we're just going to paste this in here. And I guess I haven't really talked about the semicolons yet, but semicolons are used basically like periods. So anytime a statement ends, we use a semicolon. You're going to notice on my if statements, we didn't do that because an if statement is saying, hey, if this happens, do this stuff. And so we're using these curly braces to say, here's what's going on. So the semicolon is going to finish this statement and potentially let us do some other ones. But after an if statement, instead of using a semicolon, we're going to use a open curly brace, and you're going to see this pattern repeated. The general rule of thumb is that following every single statement of code, we're either going to have a semicolon or a curly brace. Very, 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 very rarely will you have both. So for example, if I do this, which is putting a semicolon on the end of my if statement, that is a bad thing. It will generally cause you problems. It will ruin your life. You don't want to do that. So I'm definitely going to get rid of that semicolon. But you almost never want to have a semicolon and a curly brace right next to each other like that, or an opening curly brace right next to each other like that. It is perfectly fine to have a closing curly brace after a semicolon, as is happening here, because this is basically me saying, okay, I'm done with what happens when W is pressed. So those are very, very important to separate. But most of the time, we're going to have a semicolon at the end of our lines. So we've multiplied each of these by time.delta time. We want to do the exact same thing with our rotation. So we're going to do rot angle times time.delta time as well. I still have that in my copy paste buffer, so I'm going to go ahead and Control V that. Whoops, let me try that one more time. We're going to go ahead and Control V that and Control V that. So we're multiplying each of these things by time.delta time. Now, the end effect of this, if I go ahead and run my game right now, you are definitely going to notice a decrease, an overall decrease in speed. Again, that's because we're multiplying this by approximately 0.16 every time. So we're getting roughly 1/100th of our speed. And so if you notice me pressing W, I am indeed moving forward, but I am moving forward so slightly, you can barely see that movement. It is moving forward. If you look at my Z, it is indeed increasing, but it is increasing by very, very small values. Same deal with my rotation. That's at least a little more noticeable, but it is rotating really slow. So the end result here is actually I do need to change my speed. This is more now a per second speed instead of per tick speed. Tick is another fancy word for frame. So what we're going to be using, and it represents the tick of a clock. So instead of representing a per frame speed, we basically want to multiply this by about 60 to get our correct speed. And what I found for this activity, a 5 is a pretty good number here. And the rotation speed should be more around the area of about 50 or 60. So I'm going to move this up to about 60. Again, we're going to go ahead and hit play. And now my speed is better. That's actually maybe a little too slow. And again, I'm checking that wall collision. I'm not real happy with that. But my turn speed is looking pretty good here. I'm pretty happy with that speed. But we can maybe notch up our regular speed. Actually, I'm going to do that during play mode so I can test things. But I feel like maybe 7. Let's see what happens with 7. 7 feels pretty good. That's a little bit better. It's still a little on the slow side. Let's try maybe 9. I'm just bumping it up a little bit. I don't want to jump too far, but these are looking pretty good. Let's try 10. 10 feels pretty good, and I'm not doing any wall collisions, and now my movement is smooth. So I feel like 10 and 60 is a pretty good number here. So I want to remember 10 and 60. I'm going to go ahead and stop. Again, those values were reset because I was in play mode. I'm going to change it back to 10 and 60, and now I feel pretty good about where we're at. So now we're in a pretty good spot. We have written some code that is going to move us, again, along our different angles. We've learned what plus equals is. We've learned how to make a public variable, which is pretty neat. We've learned about time.delta time, which is our scaling, which doesn't really give us noticeable differences right now, but you would definitely notice it if you hit some lag or anything else. We've learned how to use a variable to deal with our speed and our turning ratios. And we've learned transform.position is us. Transform.forward is our forward-facing direction. Transform.right is our right-facing direction. So we've learned how to use the transform.rotate function. So we've done a lot today. This has been a pretty good session, and that's where we're going to go ahead and stop. So we've got, again, our goal is with today. Our goal is simply that we've got that movement working pretty nicely. Again, I can rotate, I can move forward, I can move back, and I'm moving in a correct direction based on my character's orientation. I can also get some movement turning. I can get some turns while I'm moving, which is pretty cool. And I can even do some diagonal. So for example, if I press forward and right, I'm strafing in kind of a diagonal pattern. So I do have some pretty cool turning I can do. And again, we'll get some mouse working in there later, but this is a pretty good spot. So that's about it for our forward movement. In our next installment, we're going to go ahead and learn how to fire our gun, which is going to be pretty exciting. So stick around for that. That will be our tutorial number 3. And as always, if you enjoyed this tutorial, please like and subscribe. We will see you next time for another adventure. And as always, keep on creating. Have a great day, everybody.